Today's episode is about friction.
How can I hang onto this rope without falling?
Can we reduce it so we can slide around? I'm going towards the wall! Can we increase it so I can climb a wall?
Ha ha! I did it!
Can I use it to fly? Yup! Friction! Today on Science Max Experiments at Large.
Hey, Science Maximites! Slippery. But that's okay, because today we're talking about friction. Friction is a force that is everywhere and happens when any one thing rubs against any other thing. We do lots of things to increase friction, like wear shoes with big treads on them. And we can do things to reduce friction, like the experiment we're doing today. We're gonna build a hover disc, and it's very easy. You take some cardboard and cut it into a circle, just like this. Then put a hole in the middle of the circle. You might want an adult to help you with that. And then take a plastic drink bottle cap, like this. I like use the ones that you get on sport bottles because they have a little nozzle that pops open or closed. And then you glue it around the circle and you get this. Then you need a balloon. So you blow up your balloon. I know you know that step. And then twist the balloon so it doesn't get away from you. When it's nice and twisted, you can stick it over the drink bottle cap like this, and then untwist it. And this is why I like to use the plastic drink bottle caps that come from sport bottles, because you can open it when you want. And when you do, your disc rides on a cushion of air, reducing the friction with the table, and it's almost like it's sliding on ice. You can also use CDs if you want to do a different design. Just make sure you're using CDs you never want to listen to again. Now, if any of this is too fast, don't worry. You can always go to the Science Max website, where we have all of the instructions. And now, it's time to max it out. We're going to see if we can make a human-sized, rideable, low-friction hover disc. I'm going to the Ontario Science Centre, where hopefully I have an expert that can help me. Door is stuck. I think there's a little bit too much friction with it. Oh, that's got it.
Oh no, this isn't the Science Center. Did I go back in time again?
Oh. It is the Science Center. Helena, hi.
Hey, Phil. You're here to see the hover disc.
Yes, please.
All right, come on, right this way.
So I made one in the lab that works pretty great. It's on cardboard and it has a balloon. The one you have here works on the same principle?
Yeah, it does. But you know what? My friend Russell has some ideas about making something like this, but even bigger.
Do you think we can make one big enough to ride?
Maybe, yeah.
All right, well, let's take a look at the one you have here. Oh, I see. Right, this one works the same as the one I made. It's really hard to move the disc, but if you add some air, it floats like a dream.
There we go.
Great, so let's ride it.
Whoa, Phil, not this one, the one upstairs. You can ride that one.
Oh, okay.
Yeah.
Should we bring this one just in case?
No, it's a little heavy. I think we can leave it there.
What if we need it for reference?
No, I'm sure we'll be okay.
It is pretty heavy.
Yeah,
but...
come on, let's go. Russell's waiting.
Are you sure we won't need it?
I'm positive.
Okay, but if we have to come back, I get to say I told you so.
Okay.
All right.
Hey, Ramona, you change your hair? Yeah, it's nice. It's like doing this now. Because but now it's, yeah, I like it. You should give me the name of your guy, because I wanted to, hey, oh, hey, how are you? You ever think to yourself, no matter what I do, I can't seem to get anywhere. I can't get enough traction? Well, you, my friend, need some more friction. Which one of these two shoes has more friction? Take a closer look. Huh? Right, bam. This one doesn't have a lot of treads. It doesn't have a lot of friction. But this one, it's got metal spikes on the bottom. This is called a cleat, and the spikes are for helping you grip onto the grass when you're playing soccer or golf, increasing its friction. Why do you think skis are smooth on the bottom? Come on, look at that. It's so smooth and glidey. My hand I can barely even touch the surface. It just slides right off. It's sort of glidey and smooth. They're smooth to help you glide across the snow, reducing their friction. Why doesn't this box slide down this ramp? Friction. This roller skate has wheels. Wheels reduce friction. But when I push the roller skate, how come it doesn't just keep rolling forever and ever and ever and ever? And going all the way around the world and writing a memoir. Say it with me. Friction. Louder. Friction. Can't hear you. Friction. Little too loud. Friction. Ease it back. Friction. How can I hang onto this rope without falling? Friction. How can I jump down on the floor without falling over? Friction. And now you know your friction. Your friction. Your friction. Come on. Uh-oh. Oh, Ramona, the friction sign is broken. Reset. Uh-oh.
The plan is to take our small hover disc and make one big enough to ride. So I'm off with Helena to another part of the Science Center to meet Russell, who has some ideas on how we can do it.
Oh, hey, Russell.
Hey, hi, Emma. Hey, Phil. How you doing, Russell?
How you doing, Phil?
So this is the hover disc.
This is our small hover disc, yes.
How does it work?
Well, obviously you sit on here,
Right.
Air will go into here. It gets vented through all these separate holes here, so we get an airflow over the entire area. Hopefully this will work to pick someone up. All we need is...
Air.
Oh, well, that's easy, because the small one worked like this, so we just put the balloon on, right?
I hope you got the top.
Okay, so we put the balloon on the... hold on. Larger balloon!
Oh, okay.
Sorry.
That's okay.
Okay.
Uh-oh, twist it so it doesn't...
He's losing his air.
Okay, all right. On you get.
You grab
Right.
one side, I'll grab the other.
Okay, here we go.
Go. It doesn't...
Feel way too much
It doesn't
friction
feel
on
like
No.
it still feels pretty frictiony. I think we might need something more than a balloon. So what do we do?
Well, I think we need more consistent air going through here.
Okay. So not a balloon.
Not a balloon, something, I don't know, opposite to a vacuum cleaner?
Opposite to a vacuum cleaner. That would be
Like a leaf blower.
Like a leaf blower.
a leaf
yes.
blower.
Right?
High fiving.
Yeah.
Awesome idea.
Yeah, leaf
so
blower it is.
why don't we make a couple larger discs when we'll hook some leaf blowers to them and we'll see what happens.
Definitely give it a go.
Okay, great. Carbon is an atom and is the basic building block of all life as we know it. You, me, all plants, all animals are carbon-based life forms. Other things are made of carbon too. Diamonds are carbon, coal is carbon, even pencil lead isn't lead, it's graphite, which is carbon. If you were to take all the carbon atoms in your body, you could fill 9,000 pencils. Of course, I kind of prefer my carbon where it is. Our low-friction hover disc still had way too much friction. One of the problems that Russell mentioned is that the balloon just wasn't giving enough air. But then, Helena had the idea of using a leaf blower instead. The plan now is to make a leaf blower-powered disc by starting with a big circle of wood, cutting a hole in the wood where the air will come through, and then covering the bottom with a tarp that has many holes cut out of it for the air to escape. Because leaf blowers are made to push lots of air, hopefully there'll be enough for me to ride it.
Well, this is the business. Look at
That's
this.
amazing.
It's good, right?
Oh, yeah, I love the
So-
tube. You know, high volume of air through that.
So yeah, I think it's a dryer vent I just found it in the lab. And then this, of course, is leaf blower. So I get on here, and then Helena, if you want to turn it on.
Yeah.
So once we fire it up, the air coming out from the bottom of the disc raises me up, and I float on a cushion of air.
I can't control it!
Because the friction between the disc and the floor is so low, I end up floating wherever Helena and Russell push me.
I'm going towards the wall! amazing.
Not too much control, though.
I have no control whatsoever.
Yeah, no.
But this is great. So so we have the no friction down pat. I feel we need some way to actually move.
Well, something to push you along. I was thinking as you were going, like, you need like a broom or something.
A broom. Okay, yeah. What if we do like something low friction, like a broom, and something high friction, like that we could really sort of stick on the ground?
Yeah.
That works for me.
And then we could build two of them, and we would have two discs and two ways of moving them.
Are we gonna race?
And we can race! Yeah! Okay,
Yeah.
race. That's what we're gonna do. Here is an experiment you can do at home with friction. This is a toy boat. Yes, you guessed that right. And this is a wooden plank. Correct, that's 2 for 2. I put the boat on the ramp and watch what happens. Nothing! The reason why is because the friction between the boat and the ramp is enough to counteract the force of gravity trying to pull it down. But watch what happens if I raise the ramp to the right height, the boat slides down because the friction isn't enough and gravity pulls it down. But when we change surfaces to this carpet, let's see what happens. Same angle, I can raise it higher, 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 because there's more friction between the carpet and the boat than there was between the wood and the boat. Now, if you're thinking that we're just gonna do it with a small ramp, you're wrong. Because of course we're gonna max it out. Hey, Helena.
Hey.
This is amazing.
Thanks, I made it myself.
Wow.
Ready to climb it?
Absolutely. Here we go.
Way to go.
Huh? Huh? No problem. So that was very easy.
Well, that's probably because the friction from your shoes is high enough so you don't slip.
Right. And the friction from my clothes is much lower, which is why I could slide down.
Right.
So how do we make it more difficult?
We'd probably have to make it higher.
All right, let's make it higher.
With the ramp at a steeper angle, I'll need more friction to climb up.
All right,
Ready?
I'm totally ready. Here I go. You try.
Okay, hold my drink. Here we go. Ooh.
Oh, so clearly we are not getting enough friction between our shoes and the ramp at this angle.
We should add some carpet, because carpet would add some more friction between our shoes and the ramp.
All right, let's add carpet. Sorry, here's your drill.
Thanks.
All right, carpet.
Yeah?
Same angle.
Yes.
And why have we done this?
More friction.
More friction. Let's give it a try.
Hey, way to go.
Totally able to climb the ramp. So, what do we do now to make it harder?
Make it higher.
Make it higher. Wow, it's really steep.
I don't think you're gonna make it.
Sure, if I take a really good run at it, I think I can do it.
I don't think so.
Well, there's one way to find out. No.
No.
Okay, so I can't do it. Is that it?
Well, how about Velcro,
Wow.
right? It'll give you more friction, so you can try climbing with this. We'll give you Velcro knee pads, Velcro shoes.
Velcro. Velcro handholds, Velcro knee pad, Velcro on my shoes, helmet for safety, Velcro fill, Velcro dance. Okay, you ready?
Ready?
All right, here we go. Ha-ha, I did it! Creating friction between me and this ramp means I can stay up here for as long as I... No. No, Velcro. No. No.
Phil, you okay?
Velcro! Friction! Your turn.
No.
Our hover disc worked well. So well that we decided to build another. If we have 2 hover discs, then we can race them using different kinds of friction to push them along. Something that has low friction, like a dust mop, and something that has higher friction, like a pole with rubber balls at the end. Rubber has great friction. That's why we make car tires and the treads of our shoes out of rubber.
Okay, we have a giant race course that we've set up. We've got 2 low-friction hover discs, and I'm gonna use the low-friction dust mop version to propel my hover disc. And Helena, what do you have?
I have the high-friction rubber ball stick.
Start your engines! On your marks, get set, and go!
And we're off. Remember, Helena and I are using very different methods to get our hover discs moving. I'm using a low-friction dust mop, and Helena is using high-friction rubber balls. As you can see, my low-friction dust mop doesn't make enough friction with the ground for me to push myself. Helena, on the other hand, is having no problems.
Go ahead! Defeat him! He's way back! He's way back for the win! It's the winner!
She crosses the line!
Yes!
And then we have our winner! Yes! Over the finish line, it feels way back over there.
I'm still stuck at the second turn. Way to go, Helena.
Thank
Nice.
you.
So what was the strategy? How did it work?
Well, pretty much while I was using those red balls, I was getting friction, helping me steer.
You know what? I think we need a little bit more thrust. That would work even better if we had something pushing us even harder.
Definitely.
Wait, I have an idea. Wait, hold, I need your help. Come on. I'm at iFly Toronto indoor skydiving to talk to you about friction. That's Mike. He's gonna help me out. Okay, here we go.
Unfortunately, we can't hear what Phil is saying because there's too much wind. It looks like he's trying to tell us something about the friction. Yes, he's saying the friction from the air rushing up in the chamber is enough to counteract the force of gravity, which is why he's able to float or swim or whatever he's doing. Now it looks like he might be saying even something like air can have a lot of friction if it's going fast enough. And the air in this chamber is going fast, which is why we can't hear a word he's saying. Oh, well, he seems to be having fun. So how important is friction? Well, let's say I'm out for a drive. Car tires need friction to grip onto the road. Without it, my car wouldn't be able to turn at all. But that's nothing. Without friction, the bolts holding the wheels on the car wouldn't work. In fact, none of the bolts, screws, or glue on the car would work, and nothing would stop moving or stick to anything else. Even the trees would blow away with the slightest breeze. Friction is everywhere, and without it, nothing would work.
Okay, hover disc race round 2. This time we decided to have a little bit more thrust, so Helen and I are going to be using fire extinguishers. Now, do not use fire extinguishers at home. Fire extinguishers have a very important purpose, and it's not for this, but we've got these ones special. Are you ready, Helena?
Oh, yeah.
Oh, yeah. Okay, here we go. Russell?
So, racers, start your engines. And go!
Using fire extinguishers gives us a lot of thrust. But because the discs we're riding on don't have any friction, wherever we point ourselves, we just keep going in that direction, which makes steering very difficult. Cars grip onto the road and can go around corners thanks to the friction of their wheels. When you have no friction, it's kind of like moving on an ice rink.
Oh no! I'm out! Yeah! High five! Yeah! High five! Yeah! Yeah, wait.
Oh, I ran out of fire extinguisher at the end there, so I had to cheat a little bit. So 1 for you, 1 for me, and all of them for friction.
Or the lack of friction.
Or the lack of friction. Science Max, experiments at large. What do we do next? The larger fire extinguishers?
I think so.
Oh,
Okay.
yeah.
See you next time. I know where we can get some, actually. We can go, if we go to the fire extinguisher store where we got these fire extinguishers, we can get like a...
Science Max! Gravity!
Gravity!
Gravity! Gravity makes things fall. But on this episode, I'm doing everything I can to defy gravity.
You win this one, Gravity.
From a hoop glider, to an egg drop, to a hover balloon, it's a gravity-defying dance party! All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today on Science Max, we're going to be looking at gravity. What goes up must come down. Today, gravity is the force that makes things fall towards the ground. But just because it's a force of nature doesn't mean that we have to listen to it. No! Today on Science Max, Experiments at Large, we're going to use everything in the power of science to defy gravity. We are going to be making a hoop glider. Now, hoop gliders may not look like much, but they fly just like paper airplanes. Woohoo! And here's how you can make a hoop glider. Here's how you can make a hoop glider all your own. This is what you need. Index cards, scissors, straw, ruler, pencil, and of course, science tape, which is just like regular tape, except you use this kind of tape for science. So, here's how you do it. Take your index card and cut it into 3 equal lengths. Take 2 strips, and you take your science tape, and you tape those 2 strips and make a hoop out of it. And with the small strip, you want to make another hoop. Now, what you want to do is take your straw. Now, this straw has a little scoop at the end, and that's not very aerodynamic, so we're going to get rid of that. Ooh, maybe it was kind of aerodynamic. All right, now that we've got the straw, you have to align the hoop and the straw together. So here's what I like to do. Take some science tape and stick it on the straw, and then align it so that it's perfectly straight, and then stick it on. Looks straight to me, all right? The small hoop also has to be perfectly aligned with the first hoop. So again, put the tape on the straw first, then align them up, and then start looking down through it to make sure it's aligned. There. Once you have it all taped together, you're done your hoop glider. And it flies just like a paper airplane. Pew! Awesome. So that's what we're gonna do today. Oh yeah, I gotta clean that up. We're going to max out the hoop glider. I'm gonna go meet Sonia at the Ontario Science Center, and we are going to max out the hoop glider into a giant version. We'll probably have to change the materials we use because, I don't think we can get a straw that big or cardboard, but still, we can figure it out. All right, here I go. Aha!
Oh, hi, Phil. Good. What? Pardon? You want me to help you with an experiment? Okay. All right.
Oh, Sonia, I came in.
Phil,
You came in here? I
Are
came
you
in.
okay? Are you okay?
Yeah, I'm fine. Come on, let me show you. This is what I would like to max out. It was in my pocket when I fell, so
What is that?
It's a hoop glider. It was a hoop glider. So how do we max this out?
First, we're gonna need a larger tube.
To
large
replace
tube.
the straw, yeah.
Exactly, and we're gonna need 2 hoops. So we need something that's flexible that will convert into a hoop.
Okay, that's great. So why don't we get started?
Sounds good.
All right, high fives. You may recognize this.
It is a spring, yes, good for you. But did you know that springs can defy gravity?
Ooh, oh.
Gravity defy. Gravity defy. Gravity Look at it fly! Defying. Okay, not exactly, but what if I was to hold the spring like this and let it go? What'll happen? It'll fall. Yes, it'll fall. That is true. But while it's falling, what happens to this end? Does it stay in one place? Does it go up? Or does it go down? Let's find out. I'll bring this in so you can really see it. Okay, ready? Watch close. Did you see? Did you? No? Okay, tell you what. We'll watch it again, this time in slow motion. See? The bottom doesn't move, and here's why. When the top of the spring is released, gravity and the tension of the spring are pulling on it. The bottom of the spring is being pulled down by gravity and up by the tension of the spring. These forces cancel out, stopping the bottom of the spring from falling until the top reaches it. Until there's no more tension, and then the top passes the bottom and the whole thing falls. That is how it works. But here is the real question. Will it happen differently with a longer spring? Huh? Well, I just happen to have a longer spring! Let's max it out! Bring it. Don't tangle it. So, now that I'm up high on this fire escape, let's test it out. Okay, 3, 2, 1, go! A longer spring still has the same forces working on it. The tension of the spring pulling it up and gravity pulling it down. No matter what size of spring, these forces cancel out for the bottom of the spring until the top meets up with it. So there you go, an almost gravity-defying spring! Hey, there's no door handle on this door. I guess I have to take the stairs. Whoa. Sonia and I are maxing out the hoop glider out of bigger and better materials. This is the largest tube I have, right? A giant ABS pipe and some bendable metal to make into hoops. Then we attach them all together and... Okay, big hoop is done.
And little hoop is also done.
Awesome.
Not bad.
Not bad at all. Super solid.
And that's the thing. We have pretty heavy material, so it might not fly as well as we'd like.
But something heavy can always be good, right?
Oh no.
That's what I'm talking about. See how solid it is?
Pretty
No
solid.
damage whatsoever. You want to test it?
I think we should.
Okay. I'm excited. We take our plastic and metal hoop glider outside to test it, and... Ready?
Ready?
1, 2, 3!
Huh.
It didn't really fly, did it? Sonia and I made a very solid design, but the problem with it became pretty obvious. Yeah.
It's just too heavy.
Well, that's what science is. Back to the drawing board. Here's something fun you can do if you ever get your hands on a helium balloon. Now, helium balloons float up, not because they defy gravity, but because they're lighter than air. It's because the heavier air around it actually falls past the balloon, and that ends up pushing the balloon up. But what if this helium balloon wasn't lighter than air or heavier than air? It was exactly the same. This is what I like to do. Just take a helium balloon with a long ribbon and a bunch of paper clips, and adding a little bit of weight every time. And what we want to do is make this balloon neutrally buoyant. That means it won't go up or down, but it will be neutral. You want to check it every once in a while. Let's see, 3 paper clips is clearly not enough. 5 paper clips is, 5 paper clips is pretty close. It still might float down, so you want to take off just a little bit of weight, maybe about there. Watch this. You just take the balloon and you put it somewhere,
And it stays. It stays put. It doesn't go up. It doesn't go down. It's attached to nothing. Now, let's max it out. Huh. I had a big balloon, and it was oh, there. A giant balloon. And look, it's a great paper towel delivery device. Say, did you want some paper towel? Here you go. Science.
Yeah, don't worry about Ramona. Just put him up high. Put him up, yeah, higher. Good. Hey. Grab it. Grab it. Gravity makes things fall. But where do they fall? They fall down. Oh. Towards the center of the Earth. Eh? Gravity. It fell, didn't it? So, the Earth causes gravity, right? Well, yes, gravity. Oh, come on. Everything that has mass has gravity. Gravity. But the Earth has so much mass that the gravity produced by everything else is like nothing. I mean, forget about it. But let's say I was in space with this chicken. I would have gravity, and I could exert a gravitational force on this chicken. And if I get my angles right, I might be able to get the chicken to orbit me, like a moon. Behold, my chicken moon, huh? Gravity. But let's get serious. What causes gravity? We don't know. But what we do know is that without gravity, there would be no universe as we know it. No you, no me, no chicken moon. I'd miss my chicken moon. Chicken moon, you what? Gravity. Like it or not, the universe wouldn't exist without it. You like the sign? I'll give you a good deal. Half off.
Back to our hoop glider, which was too heavy. Here's what I don't get. This is heavy, but I can still pick it up and throw it.
Yeah.
An airplane is way heavier. I could never pick up an airplane, but that can fly.
And that's because airplanes have engines, so it has a constant source of thrust. When we throw it, we just have an initial source of thrust. So we're throwing it, eventually loses its energy, therefore,
It falls to the ground. I see.
so we need something that's light,
Light
and something that's strong.
and strong. Okay, well, let's see what we can find.
All right.
Sonia and I try a plastic tube and some heavy-duty paper. We make hoops and attach them with some duct tape and run outside to try it out. Hoop glider dance! Okay, 3, 2, 1.
That's pretty good.
That was
Pretty
amazing!
good.
Let's try that again.
Here we go.
I throw the hoop glider, and although it doesn't keep flying forever, it goes much further than our first version, and also further than I could have just thrown the pipe by itself.
Pretty good.
So we've done a good job of making something that flies. Why don't we make a couple different kinds out of different materials, and we'll see if we can get one that flies even better than this.
I think that's a good idea.
Yeah, okay, let's do it. Sonia and I have created a pretty good maxed out hoop glider, but we wanted to see if different materials would make an even better one. Sonia made a much lighter version,
This time I used cardboard.
and I made this! Made a slightly heavier one.
Let's do it.
Okay, 3, 2, 1, go! Not bad. My turn.
Here we go.
Okay. That didn't really go very far at all, did it?
No.
Okay, so now we can measure it against the one that we threw before.
And
to see,
that went pretty far.
This went pretty far to see if we've got a better design here.
Here we go.
Right?
Awesome.
So, heavy one, no. Light one, no. Interesting.
No.
This design seems to be the best one. I keep thinking about how you were talking about thrust.
Yep.
All the thrust that we can put in is just what we can put in with one throw.
Yeah.
What if we could give it more thrust than that?
How can we do that?
I don't know, like some sort of slingshot or something. Like it'd have to be a pretty big slingshot.
A pretty big slingshot. But I think that sounds great, though.
I think make a big slingshot for this?
Why not?
Okay, high five. Let's do it. This is an egg. Eggs do not like to be dropped. Oh, fortunately, we can use the power of science to design something that'll keep the egg safe as it falls. Behold, my egg drop contraptions. The thing I really like about this experiment is there's no wrong way to do this. You can come up with any design you want and see if it works. This one here is a bunch of helium balloons. This structure is just to keep the helium balloons on so the egg can touch down very gently. Here it goes. Whoa. and the egg is unharmed, miraculously sound. That one worked really well. Success. This is a giant helium balloon that I think will work pretty much the same way, because I think this balloon will drop just slowly enough that the egg can actually just touch and nothing will happen. So that didn't work. And then there's this one, which has no slowing at all. It's all designed to just absorb the impact. And the idea is that the cone will crumple and absorb the force when it hits the bottom. Oh, no! Oh, no. I think it would have worked if it hadn't turned in the air, but it did, and, well, I guess the egg is completely broken. So I'd call that one a fail. This one is the parachute. You see the egg has been nestled into this foam container, and this is a parachute that will hopefully slow the egg down. Woo! Uh-oh. Whoa. Over, good. And that one seemed to work well. Yep, the egg is totally fine. The parachute worked. All right, egg drop experiment, totally fun experiment to do, but the question is, how do we max it out? And the answer is pumpkin drop. Same thing, except with a pumpkin instead of an egg. Come on. Okay. All right, pumpkin drop with everything attached all at once. Okay, here we go. Ready? 1, 2, 3. So what we've learned from this is the heavier something is, the more force is acting on it from gravity, which means the harder it is to slow down when it's falling. Okay, fair enough. You win this one, gravity, but I'll beat you next time. I'm gonna get a broom.
Being a chef is my absolute passion, and cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker. Delicious. Nothing is more important to have fresh than your seafood. It's what makes the difference between a fresh fish and one that isn't so fresh. If you live by the ocean, you probably know that the water gets high tide and low tide.
Look closely, it's the same location.
Amazing! But did you know that this is caused by the gravity of the moon and the sun? Say this cookie is the Earth, and this little happy fellow is me. Hello! And this string represents the water around the Earth. If we didn't have gravity to worry about, the water would all be equally deep around the Earth. But here comes the moon, this mushroom. Now, the moon has gravity, and that pulls the oceans towards it a little bit, like this. And that creates high tide there, and low tide here, and a little bump of high tide on the other side of the Earth. And as the Earth rotates and I'm on it, I experience low tide and high tide, and low tide and high tide. Very interesting. But there's another factor. The sun, or this lemon. Now, the sun also affects the tides, but not as much as the moon. Now, the sun does not affect the tides as much as the moon because it's much further away, but it still has an effect. If the sun was here, then the tides would be pulled away a little bit like that, and the tides would be less severe. But if the moon and the sun line up, like over here, you'd get a very, very high tide and very, very low tide. So there you are. That's how the tides are affected by the gravity of the moon and the sun. Delicious. I'm Buster Beaker, and thank you for joining me on Cooking with Science.
Our maxed out hoop glider was working pretty well.
That was
Pretty
amazing.
good. Here we go.
But we could only give it so much thrust by throwing it. So we came up with the perfect Science Max solution.
Our giant slingshot.
We pull the bungee cord back and hook it onto our hoop glider.
I am ready to fire. Count me down.
3, 2, launch it! Very nice!
Our Slingshot is amazing. By giving the glider more thrust, that is, more energy at the beginning so it's going faster when we launch it, the glider soars through the air and flies a long way.
That was great. So there you go. Giant hoop glider. Yeah, Science Max, experiments at large. Nicely done.
Nice.
What more can you ask for?
Well, my turn.
Hey, see you next time.
Science Max! Today on Science Max, it's all about the power of water.
I'll see you later.
We filter it, pump it, paint with it, and most importantly, use it to crush stuff.
Crushing!
All on this episode of Science Max, Experiments at Large.
Ha. Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large, and this is a syringe. You might know syringes from when you get a needle at the doctor, but syringes are used all the time in science because they let you measure very precise amounts of fluid. Now check it out. You push the plunger down, and it comes out the top. Or you could pull the plunger in, and it would suck more fluid in this way. But check this out. I've got a syringe attached to a hose here, and this hose is filled with water. And I wondered if the hose was really, really long, how hard would it be to push this plunger down? Of course, I don't know where the end of the hose is because it was really long and I had to string it all the way around, so, here it is. Okay, so let's find out. Push the syringe down and water will come out the other end of the hose. Pretty cool. You see, this is called hydraulics. Hydraulics is a branch of science that deals with fluids like water. But hydraulics are also a mechanism used in a lot of machines. Check this out. This is a syringe with a short hose on it, much shorter this time. And I press down on the plunger of the syringe and water comes out. And I pull in on the syringe and water goes back in. Because the plunger is airtight, it allows me to push or pull the water. But what if I close the system and take another syringe and attach it to the end of the hose like this? Well, then, if I push this plunger in, this syringe fills up with water. And then I pull this plunger out, the syringe empties. So check it out. This plunger raises and lowers based on what I'm doing with this plunger. And you know what that means? We've made a remote control. Huh? Check it out. So, if you take two syringes and you take a hose and you attach them to something you want to remote control, voila, you can build something like this. We have made our very own robotic arm that you can power remotely with hydraulics. Pretty cool, right? If you want to build one of these yourself, here are the materials you need.
First, you need two supports and the arm. I used pieces of wood, but you can use wooden spoons, rulers, or pencils. You'll need some craft sticks, elastics, and a paper plate. And of course, two syringes and a hose, which you can get in an art supply store or a hardware store.
Here's how you build your own hydraulically powered arm.
First, make the base by tracing holes for your supports the width of a craft stick apart. Cut out the holes and use a craft stick and elastic to secure the supports underneath the plate and on top. Then add some elastics and a piece of craft stick in the middle so the supports won't scrunch together.
Because we are holding this whole thing together with elastics.
Then get your syringe in there and keep it propped up with more elastics. Then get your arm and slot it in between the supports. The arm should be horizontal when the syringe is half full. Elastics to attach the arm and the syringe.
Then push down on this end of the plunger and, ha-ha, you have a remote-controlled robotic arm.
You can also max it out even more by adding more degrees of movement. You can make the arm rotate side to side. You can even add a little claw attachment at the end and power it all using syringes. Haha, science and hydraulics. So let's max it out. I just need an expert to help me. Let's see. And over and that way. Oh, Chris from Logix Academy, of course. Logix Academy knows all about building robot stuff. I'm sure Chris can totally help me. Let's go. Come on.
Oh, hey, Phil.
Oh, hey, Chris from Logix Academy. Great to see you.
What took you so long?
How long was I gone?
And what's with the orange lab coat?
Oh, it happened again. It keeps changing the color of my lab coat. But this time, Chris, I prepared for it, and I wore another lab coat. See?
Blue?
No! Well, you know what? This is happening a lot, Chris. So I wore another lab coat under this lab coat. I'm gonna have to wear a lot of lab coats, though, because this is happening all the time. We should talk about hydraulics, right?
Okay, yes,
Yeah, because we
yes.
got some cool stuff planned. Okay, so we're just gonna get the table in here. Whoa, okay. This is the hydraulic arm. Check it out.
Oh, very cool, very cool.
If we want to max it out, what can we do? We can make it bigger, we can make
What
an
if we did
arm.
it so that the force you put on this side gets multiplied so that this side's even stronger?
Ooh, what do you call that when that happens?
Force multiplier.
A force, I like that. Force multiplier, it sounds like a video game. So we would have a lot more power.
You have a lot more power, which we could do fun stuff.
Yeah, so if we had like lots of power, what would we do? We'd like crush something.
Yeah, let's crush some stuff.
Yeah, we could crush some stuff. Okay, can we start with syringes though?
Yep.
And then we'll work up as we go.
I like it.
So what do we need? Do we need different sizes?
So yeah, I was thinking we need a small.
A delicious plate of cheese and crackers, my favorite snack. But these crackers are pretty salty, so I should probably pour myself a glass of water first, huh? No! My cheese and crackers! Why? Why does this happen? Why does the water stick to the glass? Well, because of science. And the reason why it happens gets a little complicated, but it boils down to this one simple thing. Water likes to stick to things. Huh? Did you see? Did you see how it stuck? No, of course you didn't. You know why? Because it only sticks on a small scale. See those drops of water? That's water sticking to the surface. But it only works when the surface tension of the water is less than the force of gravity, which is why water drops fall when they get bigger. So it sticks to things. That still doesn't explain why you can pour water out of some containers without any drips, and other containers make it nearly impossible. It's all about the angle. Water will flow very easily when there isn't a large change in direction, like around the curved top of this glass. But when there's a big change in direction, like at the mouth of this teapot, the water can't make that turn as easily. This is also why pouring from a full glass is much messier than one that's less full. Pouring out of a full glass, the water only needs to change direction this much to flow down the side. But from a half-full glass, the water would need to change direction this much. So all this happens because water likes to stick to things. So let's do an experiment and coat this glass with hydrophobic spray. Now, hydrophobic coatings repel water. So if it's repelling the water from the outside of the glass, will we still have the same problem? Well, let's find out. Hydrophobic coated glass, non-hydrophobic coated glass, or just regular glass. Water likes to stick to surfaces, but it can't stick to one coated in hydrophobic coating. That's impressive. Should we try something else? Well, that's one way to solve the dribbling glass problem. Except you can't coat your glasses at home with hydrophobic coating because it's not good to eat. The secret is using a container that has a very sharp angle between where you're pouring the water and the underside of the glass, like this jug. And there you go. Now I can enjoy a nice glass of water with my cheese and crackers. Oh, right. Wait, hold on. I will remake the crackers into, see, look, see, it's fine. It's fine. I'm not really gonna eat that. I'm just kidding. Chris and I are maxing out our hydraulic crusher.
Yes. Before we get to that, I have a little game I want to play.
Okay, great.
Okay. You can pick either the small one.
The big
or
one.
Okay.
So what's the game?
Simple thumb war. I'm gonna press down on this side. You press down that side. We'll see who wins.
Okay, ready?
Yeah.
1, 2, 3, go. Oh, wow, that was really tough. Why was that so hard?
Well, Phila, I'm just really strong.
Wait a minute. My turn. Okay, 1, 2, 3, go. Yeah! See, pushing down on this one is way easier. You wouldn't think that the small syringe would be easier. Why is that?
The reason for it is that you have to push this one down a lot farther than you have to push this one down.
Let's see.
See how far this one goes, and this one's barely
This one
moving?
travels much more. This is how we can exchange a little bit of force over a long distance.
That's right.
To a little bit of distance and a lot of force.
That's exactly right.
Just like the lever, it's a mechanical advantage. But in this case, it's hydraulic advantage.
That's right.
Chris and I push down on small syringes, which gives us more force on our larger syringes. Our crusher was ready to go. Ooh, how about an orange? 1, 2, 3. We squeeze down and... Then we tried a walnut. Are you allergic to nuts?
I am not.
1, 2, 3. When we tried a golf ball, we reached the limit of what our plastic syringes and our hands could do. We need to come up with a stronger, more awesome crushing machine using hydraulics.
That's right. I have some ideas.
Okay, good. We can use metal.
We can use metal.
And we can
we can go bigger as well.
Ew, this water is gross, but I'm gonna drink this water. Why? Well, because of science. No, but I'm not gonna drink the water like this. First, I'm gonna use the power of science to help me clean it. How? By using gravel. Gravel, yes, gravel. So, say I've got some dirty water, and there are particles floating in that water. Large particles, your rocks, your wood. These styrofoam bits will act as the large particles. You pour it into the gravel, and the large particles get filtered out. See? Nothing but clean, clean water. Yeah, I know what you're thinking, Phil, that's not really clean yet. That's because we haven't done step 2, sand. Sand? Yes, sand. Let's say that these plastic beads are small particles. That filters out the tinier stuff. There, huh? Clean, right? No, it's not very clean. So, we filter the water in the next step with charcoal. What? Charcoal? Yes, charcoal. Charcoal works just like gravel and sand, except on a microscopic scale. Say these bits are tiny particles you can't even see. The charcoal catches these like the sand and gravel caught the larger particles. This is called a gravel, sand, and charcoal filter. The gravel catches the big particles, the sand the smaller ones, and the charcoal the microscopic ones. These kinds of filters are used all over the world to clean drinking water. Ah. Delicious. Science. Max Historica. This is Archimedes.
What? Who said that?
It's me, the narrator. We're doing a segment.
Oh, well, I was working. Don't sneak up on a guy like that.
This is Archimedes, an ancient inventor and one of the greatest scientific minds ever. One of his famous inventions was the Archimedes screw. Which was used to make holes in wood.
No, that's not what it's for. It's for water.
Right. Used to make holes in water.
What? No! Look, did you even do your homework?
Hold on. It's here somewhere.
Look, I'll just show you. You see, in ancient times, we had many uses for something that could lift water up. From a well, or to take lake water from the lake and put it into a farmer's field, and that sort of thing.
Ah, okay, I've got it from here. So, Archimedes invented a screw, and he drilled a hole in the side of that container.
No. Look, just sit down. I'll explain it, okay?
I am sitting. I'm in a voiceover booth.
Good for you. Now be quiet. Now look. What you do is you put the screw in the water like this, and then you want to raise the water higher, you see? And so turn it around like so, and the water fills each gap in the screw, and it starts to come up. It gets to the top, and look at this. Look, we've got water coming at the top there. The water is being pumped up. It is the first water pump.
I see. Still seems like a lot of work to fill a glass, but it's very cute.
No, we made them bigger. We obviously were not not going to make them this big. This is not very useful.
Right. Archimedes, one of the greatest scientific minds ever. Chris and I are maxing out a hydraulic crushing machine. We tried one out of plastic, but now it's time to make one out of metal. These are called hydraulic cylinders, and they work the same as our syringes. Small ones on this side with a lot of travel, and then a larger one on this side to multiply the force. And some mechanical advantage with a lever to help us push even harder. We tried crushing a watermelon, and it worked great.
So what else do you want to crush?
We crushed a coconut.
It's cracking. Oh, there we go. Oh, it's gonna leak.
And then a can of pop.
Science Max Cola, now in the new smaller can.
Let's really challenge this press. Perfect.
A piece of wood.
We tried to crush the wood, but we weren't able to get it to budge. So it's time to max it out even more.
I think we're gonna need like a multi-story industrial-sized hydraulic press.
You know where we can get one of those?
I do.
Awesome.
This is water.
Things float on water, like pool noodles and wood and toy boats. And now we're gonna do an experiment with how paint floats on water. How's this supposed to work again? Oh! I'm supposed to take the paint out of the can first. This is a fun experiment you can do at home. All you need is a container, some water, and paint. But not just any paint, special paint you use for hydro dipping. That's hydro, meaning water, and dipping, meaning dipping.
Carefully pour the paint on the water and add a few different colors. Then take a stick to swirl it up into a pattern.
Then you get something you want to paint, and you carefully put it in like so. But don't pull it out as soon as you get it in. You have to spread the paint away because it'll stick when you bring it back out. And then when you pull it out, whoa! Hydro dip. Let that dry, and then you have a very cool painted toy. Let's do some other stuff. This is a bike helmet.
If you put tape on what you're painting, you can remove it later to make parts that aren't painted.
Skateboard. Whoa! Oh, that's pretty cool. Now to max it out. Hydro dip pants.
Wearing the pants when you do this is super messy and not something you should try at home. But the results weren't bad.
Science pants! Science pants! Science pants. One of the ways you can experience the power of water is watching it wash away dirt. You can experiment with this yourself by making your own erosion table.
To make your own, fill a plastic tub with sand and tilt it up. Cut a hole in the tub at the low end and put a hose with a trickle of water at the high end. Then to complete your model, fill it with
A little happy town.
This small model shows how rivers cut their course to the ocean by following the lowest point. Try to design your town and the layout of the ground so the river goes around the buildings.
I'll see you later. I'm gonna take a swim in the river now.
There are lots of ways to experiment. Change the amount of water, or the steepness of the angle,
Look at the soil, it's all getting eroded over here.
or the way the town is laid out.
Every time you do it, the river goes in a different direction,
And have fun.
Oh, phew, I'm tired. I'm just gonna lie down.
and that is the power of water.
Chris and I are maxing out a hydraulic crushing machine.
What about this? Is this what we're gonna use?
We went to the Natural Resource Canada's CanMet Materials Laboratory, which is a federal research lab.
Oh, this is good. Oh, look at that! Oh, is this what we're using?
No, Phil,
Oh, I
it's
can
actually-
use this. Hold on, let me figure this out.
Maybe later.
Really?
It's just over here.
CMAT is the largest research center in Canada dedicated to metals and materials research.
This is it.
Oh,
This is it.
yeah, right! Hydraulic press. How much force does this apply?
This can do 2 million pounds,
That's over 900,000 kilograms.
which is about 20 cars.
Let's crush some stuff! Oh, crushing! We gotta get the stuff. Okay.
We started out with the piece of wood which defeated our last press.
And go!
that sound.
Awesome. Reversing.
It turned our wood into a pancake.
Whoa, totally flattened.
So it was time to try some other stuff. We crushed a ball of plasticine!
That is neat. You sort of made a rainbow.
Yeah.
Aluminum foil!
Aluminum foil.
Yes, it is now a solid plate of aluminum. And a basketball?
Basketball! Good thing we got these earplugs in because when it pops, it'll be loud.
What?
Never mind.
This hydraulic press was so maxed out, we had to think of the toughest stuff to crush. We crushed hockey pucks, a safe, we crushed a hydraulic jack with the hydraulic press.
This is a metal vise. Hard, strong,
Yeah, steel.
heavy, steel.
Whoa, look at it bend. Wow.
Now it's time to crush a bowling ball. It totally exploded. Science Max! Experiments at large, hydraulics. Whoa. Nicely done.
So fun.
I should reverse it and we should start cleaning all that stuff up,
Yeah,
huh?
I think so.
Okay, reverse.